Well, it's a great honor and a privilege to get to participate in the congratulations to Professor Sinai today and to say a little bit about his work. In the short time that we have, I can hardly do justice to the decades of work that Professor Pina spoke about. So what I'm going to try to do is just sketch a little bit about some of the fundamental ideas about dynamics and entropy and talk about which have been so seminal and so influential gosh, for I guess almost 50 years now since they began to be introduced in the 60s and 70s. So I need to start by saying a little something about what dynamics is. So let's start there. The rest of the pictures are going to be better than this. So what we mean by a dynamical system, quite simply, I'm not going to give a formal definition. I'm just going to say it's a process that moves points from one part of a space to another. So for instance, this is a sort of a cartoon of rotation on a circle. And you can see I've drawn three little points there, two close to each other and one far away. And when we rotate a little bit counterclockwise, these 2 points move down here, and this point moves over here. And this is sort of something that's pretty easy to visualize. Dynamical systems get more complicated than this. For instance, this is a picture of the famous cat map of Vladimir Arnold. So what's happening here, the space is a square, and we take points in our square, and we sort of stretch the square out into this big, long parallelogram contained within a larger rectangle of size 6 times the original square. And you'll notice that this rectangle is made up of 6 squares, each of which looks just like the original one. So what we do is we first stretch out the square, and then we take each of these 6 squares here and superimpose them on the original one. So for instance, the cat's right ear goes all the way up to the sort of middle lower part of this top square, and it ends up here, whereas the cat's left ear ends up just in this corner of this square over here and ends up in the corresponding space. So we're sort of taking this cat, we're cutting it up into a lot of pieces, and then putting them back together. So this is, I guess it's the second most famous dead cat in all of mathematical physics. And as you can imagine, this dynamical system is somewhat more complicated than what we just saw of rotation on a circle. Another thing that can happen is our dynamical system may actually involve some element of chance, which these two do not. So this is a picture of a random walk, and what I mean by that, what's depicted here, is that we imagine a particle which at each tick of the clock is going to move either north, east, south, or west, just one little jot. But it chooses whether to do so completely randomly. And so this already is a model that's of interest in mathematical physics in the sense that it models the motion of a particle in a fluid, where maybe it's being knocked against by other molecules that are smaller, that are sort of striking it from all sides and essentially pushing it in some random direction that can't be predicted at each stage. And so we see it sort of wanders around. Sometimes it sort of gets stuck in one place for a while. Sometimes it sort of moves along pretty swiftly in one direction. And it sort of traces out a complicated, snarly path like this. And this is a model for particle motion that's of great interest in physics. So maybe I'll comment, in one of Sinai's memoirs about his time in this incredibly fertile period in Moscow in the late 50s and early 60s, he writes of his colleague, Felix Berezin, that he said, mathematicians should work only on problems that are interesting to physicists. It's a very strict standard. We're going to ask Professor Sinai at the end whether he agrees with this statement. But in any event, certainly working on mathematics that's of interest to physicists has been a theme of Professor Sinai's work throughout his career. And let me just say a little bit about why dynamical systems are so important for physics, because many, many processes in physics can be modeled in exactly this way, whether it's a particle moving in a fluid or a gas, as I just mentioned, or whether it's celestial bodies moving around each other subject to Newtonian laws of gravity. All kinds of physical systems can be described in this simple way, that the input is the state of the physical system at the present time, and then some process is undertaken, and then the output is the state of the system at some time, one tick of the clock later. And the fundamental question we ask about a dynamical system is what happens when we iterate? What happens when we run this dynamical system again and again and again? Because, of course, in physics, we don't just care what happens in one tick of the clock. We care what happens in 2 ticks of the clock, or 10 ticks, or 10,000 ticks. We want to know how physical systems evolve with time. And in particular, we want to understand as best we can, mathematically, how to understand that kind of evolution of systems in general. So with that in mind, let's look at some of these systems we've discussed. So the rotation of the circle, for instance, here's another picture I drew. Let's say we know something about the particle in the past. Let's say one tick of the clock ago, it was right here within this dark black band. Then we know that one tick later, it's rotated and it's in this black band, which is of the same size. In other words, our level of knowledge about where the particle is now is exactly the same as our level of knowledge about where the particle was in the past. Our level of uncertainty has not changed. The random walk has quite a different behavior because no matter how well you know the history of the particle, no matter how well you know where it was before, there's some irremovable element of uncertainty as to where the particle is going to be in the future, simply because it is being acted upon randomly. It flips a coin to decide which way to go. And as you can imagine, the farther into the future you go, the less certain you can be about where that particle is going to be, as the randomness sort of starts to take over from the knowledge that you have. So this distinction between these two kinds of systems is exactly what entropy is about. And so here's kind of a vague definition of what now goes by the name of Kolmogorov-Sinai entropy. Kolmogorov was Sinai's teacher in Moscow. He was the first person to sort of try to formulate a definition, and Professor Sinai formulated the definition that we all use today. One way of thinking of it, it is the average amount of uncertainty about what the state of the system will be next, given complete knowledge of its history up until now. So something like a rotation has zero entropy. If we're quite certain about where the particle was before, we can be quite certain about where it is in the future. Whereas the random walk has positive entropy. There actually is some increasing uncertainty as we go farther and farther into the future. So one kind of metaphor for the way to think about what this is describing is the rate at which information about the particle's location leaks away over time as we try to predict farther and farther into the future. So, of course, this is a vague definition. There's lots of words in it I haven't defined. Maybe you want to see the precise definition. It looks something like this. Has everybody got that? Okay, this is a little bit hard to read, probably, for most people in the room and watching at home. And that's no accident. I mean, if it were easy to write down a precise definition of entropy, then it wouldn't have been the fantastic achievement that it was. And maybe this is a moment, actually, at which it's worth sort of saying something about mathematics in general, that we often talk about mathematics in terms of the great theorems that are proved. And I'm going to talk about some of Professor Sinai's great theorems a little bit later on in this talk. But mathematical progress is as much about great definitions as it is about great theorems. This is sort of maybe an underpublicized fact about mathematics. A great definition really tells us what's going on. It really drives mathematical progress. If you think about the definition of the derivative by Isaac Newton, what he would have called a fluxion, and then the definition of the notion of limit by Cauchy, which turned analysis from a sort of ad hoc subject with lots of paradoxes to something that we can really prove theorems about. The definition of information in its modern sense by Claude Shannon that sort of starts modern computer science. The definition of information or the definition of uncertainty. You'll notice that I used the word uncertainty in this vague way on the previous slide. That seems like something that would be hard to define. Well, Shannon's definition is one of the things that is one of the ingredients that's built into Sinai's definition of entropy. So these things build on each other. Or the definition of a scheme by Alexander Grothendieck, which sort of revealed number theory and algebraic geometry as different aspects of the same phenomenon. So none of these things is a theorem, but all of them are the kinds of things that really move mathematics forward. And I think Sinai's entropy deserves to be on this list too. But something funny happens when you make this definition. Let me tell you what it is. So the idea, as I say, and this is a quote from Sinai, I think from his 1962 ICM talk, where he's talking about what this was for. It was meant to make precisely this decision this distinction that I just spoke about between a deterministic system, like rotating on a circle, and something that involves probability or a stochastic system, where there's some element of chance involved. But that is not the way it turned out. So you'll notice there's one dynamical system I put on the slide, which I haven't discussed yet. So let's bring back the cat. And Sinai proved something quite remarkable. He showed that maps like the cat map, not just this particular map, but a whole class of maps called, and also have diffeomorphisms of the torus, they have positive entropy, like the random walk. Now remember, this map was completely deterministic. There was no coin flips, no random particles. You could write down an algebraic formula for this map. It's completely deterministic, and yet it behaves as if there was some randomness going on. And this discovery really sort of changed the whole vision of what dynamics was about. And it's sort of, in a way, one might say it's the beginning of the study of chaotic dynamics. So just to sort of see what's going on, this is a picture of iteration of the cat map. So there's the cat again. There we cut it up again, and it looks like that. But now we take the pieces we cut the cat into, and we cut them again, and put them back together again, and it ends up looking something like this, and again, and again. And you see the level of catness of this picture has notably decreased. Okay, there's no formal definition of catness, but the point is that somehow it does seem that even points that start out very close together on the cat may have gotten quite far apart by step 4, and certainly by step 10 or by step 100. So the way you should think of this is, even if you have a lot of information about where you start, that information may leak away over time, just as if it was a random walk. And this is what Sinai spoke about in Stockholm in 1962 when he spoke at the ICM. So one hallmark of a really great definition is that it applies to more things than you originally intended. So, I mean, for instance, and it gathers together different phenomena that may look on the surface very different. So, for instance, Newton's understanding of gravity, we knew before Newton, right, that if you dropped something, it fell down. And we knew that heavenly bodies moved in roughly circular orbits. But after Newton, we knew that those were two manifestations of the same phenomenon and could be described in a common language. And of course, that radically changed our understanding of physics and our understanding of both of those phenomena. So here I have a picture of something which does not look at all like the pictures I drew in the first few slides, but it is also a dynamical system. It's called a Bernoulli shift. So here, our space of states, instead of being a point on a space that I can draw on the slide, it's an infinite string of bits, of ones and zeros. So it's something that looks much more like something that might come from theoretical computer science than something that might come from physics. And our way of measuring this dynamical system is to look at what number is in this box. So right now, if I do a measurement, I get 0. And what's my process? How do I go from one state to another? It's very simple, actually. I just shift. I just shift everything to the right. So if I measure, I get 0. If I shift everything to the right and measure, I'll get 1. If I shift everything to the right again, the 0 will be in the box, and I'll get 0, 0, 1, 1, etc., etc., etc. So in this system, the measurements that are in the past are precisely all the numbers that are to the right of the box. And the measurements that are still in the future are precisely those numbers which are to the left of the box. And the measurement I make right now is in the box. And because these bits are chosen independently, this is a system which has yet a different behavior from the ones that I've discussed, because the past has no bearing on the future at all. Whether the numbers to the left of the box, that way is left, are 0 or 1, has no bearing on whether the numbers to the right of the box are 0 or 1. So this, if you like, is a dynamical system. It's all entropy, if you like. Knowing the past gives you absolutely no information about the future. And this is only one example of a Bernoulli shift, by the way. I mean, you could imagine other things where there were more choices than just 0 or 1, or maybe they were drawn not equally often, but under some probability distribution. But the point is, this is some class of dynamical systems which is fundamentally digital, or in the words that Professor Pina used, symbolic dynamical systems, things that are discrete in nature, not continuous. So the first great thing is that these kinds of dynamical systems are subject to the same kind of notions, and the notion of entropy makes sense in this context too. But more than that, let me just mention one extremely striking theorem of Sinai, which is the following, and I have to put on a condition that I'm not going to describe too much. An ergodic dynamical system can be expressed as a combination of two parts, which are mixed up in some funny way. And one part is completely deterministic. One part looks like rotation on a circle. It has 0 entropy. And the other part is a Bernoulli shift with the same entropy as T. Now, this is quite remarkable. Again, let me say, we may start with something that's completely continuous. We may start with something that completely comes from physics that may display some kind of chaotic behavior, like the cat map or something like that. And the remarkable theorem is that we can capture this entropy. We can capture the evolution of this system by something that's digital, by something that's symbolic, that's not continuous at all. So this is really the first step in what you might call the classification of dynamical systems. And it shows that that this entropy is really a fundamental invariant, a fundamental quantity that captures something about the dynamics of the system, whether it comes from computer science or comes from physics or comes from somewhere else entirely. So the last of the ideas I want to talk about today is Professor Sinai's work on billiards. It seems like not everybody knows there's an entire branch of mathematics devoted to this game, but there is, and Sinai is essentially the founder of it. Let me explain where this comes from and what it has to do with physics, and we go back to Ludwig Boltzmann and the beginning of statistical mechanics. So if you study a gas, one good way to study it is to think of it as a substance that has continuously varying qualities. Maybe it's denser over here, less dense over here, maybe it's under higher pressure here, less pressure here, it's hot over here, it's cold over here, et cetera, et cetera. These are continuous quantities that you could measure with numbers, and then you could use calculus. You could use the language of differential equations to describe how this gas evolves over time, what happens to it. And that works extremely well. But the problem, of course, is that that is not what a gas actually is. Things in real physics are not continuous, and what a gas actually is a whole bunch of molecules that are sort of flying around in some enclosed space and like banging against each other. And so the fundamental question is, can we reproduce, can we show that the behavior that we observe of gases can actually be derived from what we know about these small interactions at the microscale between molecules? And in particular, Boltzmann hypothesizes that in some sense you can imagine that these molecules in the gas are placed randomly, by which he means that if you let the gas sit in the bottle and fizz for a long time, that essentially every configuration of molecules is as likely as any other. And Sinai's work on this, he's really the first to kind of place this kind of question on a rigorous mathematical basis, even to formulate a question that can actually be precisely answered, yes or no. And a key element of his strategy is to do what mathematicians always do when studying a complicated physical problem, which is to simplify. Or more precisely, to simplify without oversimplifying. So what does this mean? You may say, like, 1 million particles seems kind of intimidating. Maybe we can sort of understand the problem with fewer particles and see if we can sort of understand some of the features. And what's remarkable is that even if you consider just one particle, many of the fundamental difficulties of the problem are still there. That's quite remarkable. So let me show you a picture of what's called the Sinai billiard. Here it is. It turns out that billiards on a rectangular table is not quite complicated enough to capture the feature of the way gases behave, but a square table with a hole in it that's shaped like a circle, that's enough. So the picture you're seeing here is I make a billiards table that's square, I make a hole in it, and then I shoot off some billiard, and it just kind of goes along doing what it does. Every time it encounters one of the flat edges, it reflects the way flat edges reflect, and it's bouncing here. And then when it hits the circle, it bounces off the circle, and so on and so on and so on. It makes this route all around the table. And then you can start to, so you're imagining like a gas with only one molecule. But you can still ask the kinds of questions that statistical physics wants to ask. For instance, you can ask, and this is a question, again, I won't define ergodicity, but this is sort of the idea. You can ask, is this path of the billiard going to fill up the whole box? And more precisely, is it going to fill up the whole box with a uniform density so that the billiard ball spends about equally much time in each little sector of the square? And that turns out to be quite a hard problem, even for just one ball. Or you could ask a problem that's sort of more in line with what we discussed about entropy, which is if two balls start out very close together and with very similar velocities, will they stay close together and with similar velocities? Or over time, will the information that they were close together start to be forgotten, and will those two billiard balls become completely decorrelated from each other? And it turns out that the answer, and this is part of what Sinai proved, the answer to both of those questions is yes. In other words, for this very simple model of a gas, Boltzmann's expectations about how statistical physics is supposed to behave were validated. And this work touched off, well, as I said, an entire field, both containing many further results by Sinai, but also like many other people and continuing to the present day, and it remains an active subject of research. So let me just finish. As I said, I'm only up to 1970, So I've hardly touched on many of the great works of Sinai. Let me just sort of mention a few more things, which I won't say so much about. There's a famous paper in the 90s with Bunimovich and Chernov where he proves much more general theorems about billiards in 2 dimensions with potentially many particles, not just one. I don't want to make it sound like he was content to stop at one. A beautiful paper with Lee about the Navier-Stokes equations, the most fundamental equations in mathematical physics governing the motion of fluids. And maybe I can't resist mentioning a very recent paper with his student Celerossi. I'm a number theorist, so I think of, which means that I do the kind of mathematics that's not interesting to physicists. But even here, dynamics comes into play. And so in recent work, he's been studying dynamical systems which involve, of all things, factorizations of integers into primes. And even there, one can see the reach of these amazing definitions and ideas of Sinai. And finally, maybe I'll close just by saying that mathematics is not only about definitions and theorems. Sinai, as I mentioned, comes from this incredibly fertile group of mathematicians studying in Moscow, centered around Kolmogorov in the 50s and 60s. And Sinai, in the decades since then, has generated his own school, advising dozens of PhD students, and really, in some sense, creating the next generation of dynamicists. So for those of you who know the subject, you see that just to list, and these are only a few of the many great students who he's advised, but Anatol Katok and Marina Ratner, Gregory Margulis, Bunimovich, Chernov, I mean, these are really the people who are bringing this subject into the next century and who have their own students. So he has been creating this field both by proving amazing theorems and making amazing definitions, but also by training the next generation. So with that, I'd just like to ask us to congratulate Professor Sinai one more time on the awarding of the Abel Prize.